I'm the director of research at Lightricks. Not that I can actually see you, but who knows Lightricks and what we do? Yay! Okay, so it's not no one. I'll present the work that we call Clear Skies Ahead. It's joint with Tavi Halperin and Hillel Kain from Lightricks and also Mike Verman from the Hebrew University. There's not a lot of time. I'll just go over the main thing going on here, and you can see the paper on arXiv, or if you're in Eurographics in May, we'll present there. The work is about sky replacement in videos, but I'll talk a little bit about stills and about real time and why it's hard and important, and that's part of the challenges we deal with. So I'll first start with why are we talking about sky replacement? Why is it even interesting? It's not always so obvious. And then about changing and compositing skies onto still images, videos, it's a whole different monster. The segmentation pipeline that we used, that's something I'll try and focus on, and a couple of examples at the end. So why sky? Basically, when we look at outdoor images, around 50% of the pixels, sometimes even more, sometimes a little bit less, are sky. And in the last couple of years, there's more and more attention to stuff and not just objects. But when you look at an image from an aesthetic point of view, you want the skies to be as realistic as possible and aesthetic and sometimes even dramatic. And they're not always that pretty. So we developed a pipeline to replace skies in still images, and we put it in one of our products. We create content editing and creation tools for mobile and web, and QuickShot got this feature about a year and a half ago, I think, and the excitement was really off the charts. The motto for the app became photography beyond reality, because people were sending us photos of them in, hazy and wintry conditions all over the place. Weddings ruined, and then they fixed all their photos. So it is of interest to people. So basically, the problem here is a problem of composition. You have your image, and you want to put something on it and make it look good. Not like this, but actually good. So the first part of a composition is to get a mask of what you want to cut out and what you want to leave in. So surprise, surprise, we trained a neural network in order to segment the skies. Like I said, we started working on it about 2 years ago on still images. And stuff were not a big thing then. Cocoa stuff, panoptic challenges, segmentation challenges were not a thing yet. So most of the data, the data was pretty scarce and it was not very good. But neural networks are good in averaging out errors, and you can do some augmentation and get nice results. But nice is not good enough. It's not good enough for a product. It's not good enough to look real. So we went and checked what are the main issues. So one thing was darker skies, night skies, and dark scenes in general, but the other one was actually clouds, because clouds, even if they're a different category or if they're part of the sky, they have a lot of variability, and they don't always look the same. They're not all white. They can change the scene, and the network was really failing at that. So basically, we just took clouds, either real clouds with transparency or simulated clouds. You can use Pearly noise in order to make clouds. There are very realistic ones in games, and just added them onto the ground truth, where we had sky segmentation. And as you can see, it depends on the ground truth itself. It's not always very realistic. It's not the nicest looking image at the end, but it is a big difference maker. And while it's not, again, taking like a generative model and making the whole image look real, it doesn't really matter. Even this very simple trick of augmenting the data got us from, and these are like 2 cloudy images, got us from pretty much fails on these types of images onto that accuracy. And there are all kinds of numbers here, but if anyone ever did segmentation, you know that mean IOU is not the whole story. The story is usually whether there are holes, whether the boundary of the object, the skies here, are accurate or sharp. And that's where actually the big difference came from augmenting the data in synthesizing more examples and varied examples, and not just adding like color changes and the whole regular things that you see around. The second part is taking the cover sky. You have some asset or procedural generated skies, it can be just about anything, and stitching it onto the non-sky area of the original image. But as you can see, if you just stitch it, even if the boundary is very accurate, the results don't look very realistic. I mean, at the top you can see that the water don't reflect the new sky. So the way to deal with that is actually, it can be very complicated, but it can also be very simple. We used a mass transfer in RGB to take colors from the skies onto the original image and blended it in a way that mostly changed the ambience, the ambient light, so where reflections are more apparent, you get a little bit more of the ambience, and all the rest is just colored in. And that's basically what we had in QuickShot and in still images. And then we said, why not do it in video? We have a video editing product. It's a bigger challenge. So what are the challenges in video? The first one is temporal consistency. As you can see here, the result in mean IOU is pretty great, but any flicker is something that the human eye catches in like an instant, and you can't afford to have flickers, you can't afford to be inconsistent between frames. So that's one big challenge. The other one is runtime. Because all our algorithms run on device, then a video, if a video is 1 second and it has 30 frames per second at, let's say, 720p, then you don't want the editing of the video to take 5 seconds or 10 seconds. You want to actually do it at the same frame rate as playing it. So you get 34 milliseconds for a whole pipeline that I'll describe in a second of segmenting and coloring and everything else in a 720p image. The same thing goes for color transfer and ambience, because the scene itself is not static anymore, and new objects with new colors can come into the scene, and you need to make it so it's kind of a linear progression of coloring. And there are also other issues in video. One is exposure and vignette correction, because unless you fix the exposure of the camera, then all of these should also be applied, all of these changes should also be applied to the sky cover that you're using. And field of view estimation and camera viewpoint tracking in order to actually match the motion in the cover to the motion in the original video, because any difference in motion is very, very noticeable. So this whole thing, it's a pretty big pipeline. It's a systems paper, right? So it has to have a big pipeline. The base video needs to be composited with something taken out of a 360 image or 360 video. It can also be a panorama that you build ad hoc. That way, I mean, in the paper we show how to do HDR video by doing actually 2 videos and then compositing them together. So the original video goes into the segmentation, and all the tracking and estimation and exposure estimation is done and applied on the cover. Color transfer is calculated and applied by the specific mask, and then you composite it. And there are no Poissons being solved here. There's nothing that takes a lot of time because the boundary has to be very accurate, and some image processing tricks are used to mask any inaccuracies, actually. The last thing is what we used in order to get temporal consistency in the segmentation network. It's pretty interesting. We used a feedback loop, so actually the network gets 4 channels. It gets the RGB of the image and another channel of the feedback loop of the segmentation from T-1, basically. And that's the way we get much more consistent results. But it's very, very hard to actually make this kind of architecture work, because if you just start and train it, then these kind of things happen. Basically, the network is trained to believe the feedback loop, and it seeps in like a segmentation cancer, kind of. And yeah, that's what we called it. And you get, like, once the network does even one mistake, it kind of thinks, okay, so this was colored white, this is 1, this is true, it's segmented as sky, so it's got to be sky, and it believes it on and on, frame by frame. So you really have to kind of shake the belief of the network in the feedback loop. It's not just training with an empty feedback loop, which are the initial conditions also for the network, but it's also adding noise, and not just Gaussian noise, also like blobs of noise, big blobs in all kinds of areas, extending, dilating the boundaries, warping and morphing, and all kinds of things that actually mimic the errors that might occur in a real video and a segmentation. So just as a final result, if this is a classical video because it actually rotates and doesn't translate much, and again, details about all the tracking are in the paper, then this, and if you have a quick Hawkeye, then you might have seen that the first frame had like a little bit of white, so the first frame, the segmentation wasn't very good, and then we actually run it again to get better segmentation using the feedback loop, and then all of this is very, very consistent. And this is a tracked cover from a still 360 image, and since we're running out of time, this is a composition result. And actually, I see that one video is missing here, but sometimes, I mean, people are looking also for dramatic effect, for non-realistic effects. Put a whale in an aquarium, like swimming in the sky. One of our ads for the new Video Leap, the video editor app, will have it, probably. And as always, if you're interested either in this or in research at Lightricks and editing mobile apps, so it's serious research for fun stuff, you can reach me at Ofir at Lightricks, and I'll also be here.